At classification, first steps, what a training set is, what a test set is, how to learn, how to predict the correct label from a training set. We looked at the k-nearest neighbors classifier as a first algorithm and noted that it does quite well, but it's heuristic in nature, and so we were out for something more principled. And in that spirit, we discovered statistical decision theory, which, however, requires knowledge of the true densities, which are generally unknown. So here was an example I showed, a summary of statistical decision theory. We have, so if we did know the true class densities, we could put them in the numerator. From those, we could compute the complete density, which is in the denominator, and that would give us the posterior. So the posterior probability of finding class 1 or class 2 at a given place in feature space. And if we follow this rule, then for a given loss function, we obtain the best possible classifier, the base classifier. Do you have any questions regarding last time? Exercise was okay? Too much programming? Too little programming? Okay, so either everybody's asleep or everybody's perfectly happy. I assume the latter, of course. Then for today, I want to discuss a couple of measures that describe the association between variables, linear and other. Then I want to introduce the normal distribution in multiple dimensions, and all that is a preliminary to then do linear or quadratic discriminant analysis. So that's also a classifier, but in many ways it is complementary to k-nearest neighbor classifier. So if we have looked at those two, we have gotten to know two extremes. If time permits, at the end of today, because we talk about the normal distribution quite a bit today, I will also introduce Gaussian graphical models, but that is more of a preview for things that will come towards the end of the semester. So, describing or measuring the association between random variables. So the official reason to talk about this is to get to know the covariance, which we need as one ingredient for the multivariate normal. But I will also discuss a few less standard association measures just because they are important and it is a good place for me to mention them. So just as a reminder, the variance of a single random variable is defined as follows. And we have a similar definition for the covariance. So the covariance is a measure of the linear association between two random variables. And you will see when I show you examples why this restriction or why this adjective here is important, because random variables can of course be associated in nonlinear fashions, but that can not always be discovered by covariance. So if we have two univariate random variables x and y, the covariance is defined as x minus the expectation of x minus e of x times y minus e of y. there are alternative ways of writing down this result. So we can multiply this out, and we'll find that okay, and now if we take an expectation of the random variable x with respect to x, an expectation of random variable y with respect to y, this is just a number and that is just a number. So these are scalar numbers. This is a random variable, but the expectation of that is no longer a random variable. This is a normal number. And if we take the expectation of a normal number, this is just the number itself. So in other words, this expectation of, I can cancel this, okay? So this is just, if I pick up this last term, this is just the expectation of x times the expectation of y. Now the first term is also easy, I just copy it down. And here we can make the same argument. So the expectation of x is the same as just the expectation of x, which I can then, so this is a number which I can pull out of the expectation, and what remains is the expectation of y. And here similarly we have e of x times e of y. Okay, and altogether, so those are the same terms. We have minus 2 plus 1. Overall, we get so this is equivalent. The only practical difference is if you have, let's say, two long time series, x and y, and you want to compute the covariance. The first formula does not allow you to do it on the fly. So you have to first pass through your data once to compute the expectation of x and the expectation of y. And then you can insert those into the formula, and then you need to go over your data a second time. Whereas this second formula here, it allows you to access your series of data just once in a single pass. Okay? And nowadays that processors are much faster than hard disk access, such details can matter. Okay, so this is the definition of covariance, and well, you see it looks very similar to the variance, and in fact, the diagonal elements of a covariance matrix, or if I write, so I could equivalently write the variance of x as the covariance of x with itself. So if you insert this rule, you can deduct a couple of properties. For instance, you can look at the covariance of a sum of random variables with another sum of random variables. So these coefficients A are just scalar numbers. And this covariance of sums of random variables is the same as the sums of the covariances themselves. And if you prefer, you can that's fine. So you can verify this by using the definition we've seen. But this formula now is useful if you're interested in computing the variance of a sum of random variables. Because importantly, this is in general not the same as the sum of the individual variances. We can see that using this formula. So we can look at the variance, the sum of these random variables xi. Now I can rewrite this as above. So the variance is, I can rewrite as the covariance of the sum of random variables with itself. But I'm using a different index now so that we can distinguish these two. Okay, and by the above formula, this is the same as and we can now single out the diagonal elements and well, treat the diagonal and the non-diagonal elements separately, keeping in mind that the covariance matrix is symmetric by definition. So we have this bit, which is the same as the variances, plus I have all these off-diagonal elements. So I'm now looking just at 1/2 of this covariance matrix. And because I'm looking at just 1/2, I need to take into account this, well, the fact that I have 2 halves, so I have a factor of 2. Okay, so you see that the variance of a sum of random variables is, I'm writing this really explicitly now because if you're woken up at 3 in the morning, you need to remember that. So the variance of a sum of random variables is the sum of the variances of those random variables plus, however, these covariances. And remembering that, well, covariance is a measure of association, we can say that whenever we have correlation between these random variables, those two terms are different. Okay. So far, when I talked here about x and y, these were always univariate random variables. But sometimes we have random vectors. And if we now use matrix notation, we will assume that we have a random variable which lives in a p-dimensional space. And we can then use the following definition. So now I just write the covariance of x. So before, when I had univariate arguments, I always had 2 arguments. A first argument and a second argument. And this time I'm just using this random vector as a single argument. So covariance of x is then given by the expectation of So this first vector here is of dimension p by 1. And the second vector is of dimension 1 by p. So overall, I get a matrix that has dimensions p by p, the covariance matrix. And we can look at an expression similar to this one here. So what happens if we transform our random variables by some matrix? So A is now a matrix, let's say with dimensions q by p, and X itself is still p by 1. Then we can just insert this in the definition. So I will get, wherever I had X, I now write AX. And now I can factor out some of these A's. So A is not a random variable, so it has nothing to do with its expectation, meaning I can pull that in front of the expectation operator. So I have E times the expectation of and on the other hand, keeping in mind this transpose operator here, I can pull out A transpose on the other side. And that was just the definition of the covariance itself. So overall, I find that the covariance of AX is the same as A times the covariance of X times A transpose. So that's a very convenient formula whenever you take some linear combination of your random variables. In matrix notation, you can conveniently see how that transforms the covariance structure. So far, we talked about random variables. In practice, we just have a finite data set. So we only see realizations of those random variables. So we should look at how we get an empirical estimate for the covariance. This empirical estimate comes by name. It is called the sample covariance matrix. And well, the way it is defined, instead of the expectation operator, we put an average. So we put n over something. So all of these are vectors. I'm using small letters, but all of these are vectors. I'm using small letters now because these are no longer random variables, but realizations thereof. Now, 1 over n is what you would use if you, just use the definition of the expectation. However, to get an unbiased estimate, one should put a -1 here. So this fact, or the coefficient n-1 is used because it gives you an unbiased estimate. There are 2 exceptions, namely if the mean is known rather than estimated from the data, or if the data is known to be to follow a Gaussian distribution. The Gaussian distribution is so normal in statistics that they call it normal. So if the data is normal, then in those cases, instead of using n minus 1, people use just n. And this sample covariance matrix itself has a relative, which is the scatter matrix. So if we forget about this normalizing factor and just look at this part here, this is called the scatter matrix. So I'm introducing all these terms because you will find them when you read papers and read books and so on. So the scatter matrix S, well, it's the same as above, just without the normalizing factor. We can write the same in a somewhat nicer notation, namely by using the centering matrix. So I can equivalently write this as XC and X transposed with the centering matrix defined as follows. This is the identity matrix minus, so identity matrix in an n-dimensional space, minus 1 over n multiplied with 1 transpose. And 1 is simply a vector of 1s. In fact, n by 1 1s. So I could put subscripts n everywhere here if I wanted. So this is an idempotent matrix. If you apply it twice, it remains the same. That makes sense because it subtracts the mean, and if you subtract the mean from a set of values from which you have already subtracted the mean, nothing else changes. So it's a projection operator. And if you know that your data is already centered around 0, then you would just write XX transposed without this matrix here. Okay, but if your data has not been centered to the origin of your coordinate system before, then this is the proper thing to do. We will see this matrix later today, but also later in the semester when we look at multidimensional scaling. So that's it's an interesting matrix. Okay, so okay. I was afraid you were going to say, could I write more nicely? That is very hard. Bigger is not a problem. So where exactly here? It means more wiping of the board for me, you see? Okay. Yeah, please keep complaining, okay? Whenever I get too small, tell me, and I will try and make amends. Okay. So far so good. However, covariance has shortcomings that I want to talk about now. Some of those we can lift easily, others are harder. One of those shortcomings, or let's call it features, is that covariance is scale dependent. So the covariance of A times X and Y equals A times the covariance of X and Y. So in other words, if you compute let's say x is the length, and it matters if you measure it in millimeters or in kilometers. At least it matters for the covariance. However, such scale dependence is a dependence that can easily be defined away, in this case by using the correlation rather than the covariance. So the correlation, or more precisely the Pearson type correlation, is simply normalized to lift this scale dependency. So it is scale independent. The correlation between x and y, which is typically abbreviated with a rho or sometimes with an r, is defined as the covariance divided by the standard deviation of x times the standard deviation of y. And it has the following properties. It's always between -1 and 1. If it is either 1 or -1, this implies that the two random variables are strictly linearly dependent. So for instance, this can mean that x is just a multiple of y plus a constant. When we have a rho larger than 0, we call the data correlated. When we have a rho smaller than 0, we call it anti-correlated. And when it's approximately 0, we say it's uncorrelated. Okay, now you know what comes next. Whenever people talk or especially teach about correlation, without fail, they must mention that uncorrelated does not mean independent. Okay, so uncorrelated does not imply independent, except in special cases. So in general, what is independent? We haven't talked about this yet. If we have a random variable x, which is independent from a variable y, this means that if we look, for instance, at their probability density functions, assuming those have continuous distributions, this is the same as saying that the joint probability of x and y, sorry, I should use realization, so these are small letters, is the same as the product of the marginals. Or I can write this differently. I can say the p, and now I'm using capital letters to indicate that these are the random variables. Pxy is the same as px times py. So just to remind you, this is the joint, and these are the marginals. By the way, this also holds in the reciprocal domain. So if we take the Fourier transform of a probability density function, this is called the characteristic function of a random variable, and some operations become more convenient in this reciprocal domain. So I'm expressing the same now in terms of characteristic functions, and if fxy is the characteristic function of the joint distribution, independence implies that it's the same as the product of the characteristic functions of the marginals involved.
So covariance is 0 for independent variables?
When the variables are independent, they have a covariance of 0, but not vice versa. Okay, so if we have that, it follows that the covariance of x and y is 0. And the important point is that the reverse is not true. So let's look at a couple of examples for this. We have a couple of distributions which somebody on Wiki has kindly plotted for us. And we have associated with them their Pearson correlation coefficient. So this is the kind of distribution that statisticians like. This is a normal distribution which is just oriented at different angles. So here we have a perfect linear association. So one random variable, so y is x in this case. In that case, y is minus x, and we have correlation coefficients of +1 and -1 respectively. Here we have a lot of linear correlation. Here we have some linear correlation. Here we have 0 correlation. And then there are a couple of more exotic examples down here, and they have been constructed so as to have 0 correlation whilst being far from independent. Okay, so clearly we have some dependence between x and y here or here. So please tell me which of these distributions here are actually independent and do not just have 0 correlation. I should probably offer a cool drink for each one that you discover, and you pay me a cool drink for each one that you mention falsely. Otherwise, it's unfair, right? Go ahead.
In the last line, the second and third ones are independent, the square ones, and the last in that line.
So the random variables or the axes are defined as, really the horizontal and the vertical axis. Yeah, because I think you in your mind, you rotated the coordinate system, which, humans are great at doing. And actually this is, people try very hard to give computers the same invariance that you have built into your visual system. So in fact, using this perpendicular coordinate system as it is, so just the horizontal and the vertical axis, this one and that one are not independent. Huh? But you mentioned one more?
The last one.
The last one. That's correct. So we have, if we looked at the marginal distribution here, this would be, 2 bumps like a camel and another 2 bumps. And if we multiply these marginals, we find this joint. Any others? Yeah. Do you want to add or explain why? Anyway, it's correct. So I know, because I've been reading in the description, that in the first line these are all Gaussian distributions, and it so happens that for a Gaussian distribution, for normal distribution, 0 correlation also implies independence. Yeah, maybe. I also tend to say so, but I think there's, this is somehow a technical limiting case, because while we have a nice distribution for the second random variable, the other random variable can just take a single value, which I think is also the reason why no number has been given here, because you run into some technical problems. But qualitatively, I agree with you that yes, this would also be independent. Okay, good. I can give an analytical example instead of showing these pictures. So we even have space on the other board. So this is a counterexample making the point that zero covariance does not tell us that we have independence. So the example is a little contrived, okay, it's just to make the point. We have x, which can take the values -1, 0, or 1, and we have a random variable y defined as the square of x. So this is a perfectly deterministic function. If we know x, we can exactly predict what y is going to be. And now I want to invoke the formula. I'm going to use this formula here for the covariance. So we need to look at this expectation of x times y and then the other term. So the expectation of x, if it can be -1, 0, or 1 with equal probability, the expectation of x here is 0. And the expectation of x times y, inserting this definition here, is the same as the expectation of x to the third. And again, if they have the same probability, then that is also going to be 0. And hence, the covariance is going to be 0, even though we have this perfect nonlinear relation between the variables. Okay, so if you plotted the values we can have, here we have x and y, and the values which we can have are those. So in general, when you have such banana-shaped distributions, provided you get the symmetry right, you will have 0 correlation, even though you clearly have some dependence between the two random variables. Okay, well, let's stick to the correct breaks, at least this one time. We'll have a 10-minute break, and then we can look at other measures of association before moving on to the normal.